Hopefully you had fun with that integral. Did you catch the integration by parts? If not, you probably have to go back and do it again. I'm just gonna run through it quick in case you needed help with a couple of the steps. If you were good with it, you can fast forward to when I start to talk about over there real quick. I chose to split the integral into the two pieces, so I've got the part that I can integrate normally and then my integration by parts separate. So my normal integration, right, 2x cubed becomes 2 over 4x to the fourth, minus 2x becomes just minus, we would just get x squared, the 2 will cancel out, and then e to the x stays e to the x, so then I just have minus e to the x, and in a minute we'll evaluate all of that from 0 to 1. But then over here, notice x times e to the x is one of those classic, there's this product that we can't just integrate over, you can't split it over the products. Instead, we have to figure out other ways to do. And one of our classic ways to deal with products is to do integration by parts. So we have to pick our u, and we have to pick our dv, and then from our u we'll get a du, and from our dv we'll get a v. So remember, u you're trying to pick is sort of the most complicated part of the integrand that you can differentiate, whereas you keep, and it will get simpler when you differentiate it, versus dv, we're going to keep kind of the most complicated part that we still can integrate, because remember, to get v, you have to integrate or find the antiderivative of dv. So typically we keep e to the x as a part of the dv, so dv is going to be e to the x. Remember, we always keep dx as a part of dv. So when we integrate dv, really we'll be doing that little integral of e to the x dx, which is e to the x. Normally there'd be a plus c, but it's not necessary during integration by parts. So v is e to the x. That leaves u, so choosing e to the x dx to be dv leaves x as u. So you've got that x is going to be u, and then our du will be differentiating that, which means it's just going to go away, but remember we are left with a dx. So then over here, when we put that in with our integral over here, we'll have a plus. Remember, you have uv, which in this case is going to be u is x, v was e to the x. That part will also get evaluated on the bounds because this is a definite integral. So we have uv minus the integral, remember we do v du, so v is e to the x, and then du in this case is just dx, and that integral keeps the same bounds of 0 to 1. So now we just have to clean up all of this and simplify it. And now you'll notice our integral has become much simpler because now the integral of e to the x is just e to the x. So all in all then we're going to just get, when I plug in a 1 up here, really this is just a 1/2, we'll get minus 1 squared, which is 1, minus e, because e to the 1 is e. Plugging in 0, be careful it's not all 0, because we're going to get minus, the first part 0, minus 0, but e to the 0 is 1. So we get a little minus 1 there. This piece, plugging in 1 gives plus 1 times e to the 1, which is just e, and then plugging in 0 does give me a 0. And then when we take the antiderivative of e to the x, we're going to get e to the x. So it will be minus e to the x evaluated from 0 to 1, which once I clean all of that up, so in the first part, we just got a 1/2. I'll just keep the non-zeros, minus 1, minus e, minus a negative 1 will be plus 1, and then we've got plus, oops, this should be e to 1, so plus e, and then we'll have minus e to the 1, and then minus the negative will be plus, remember e to the 0 is a 1. So a bunch of stuff here is just going to cross off, right? We've got a minus 1 plus 1, minus e plus e. So really I've got 1 and another 1/2 will be 3 3/2, and then minus e for our integral there. So hopefully you got there to 3/2 minus e. It takes a little bit of going back to Calc 2 to remember that integration by parts. When we're taking a look at a question like this, so we did an integral in terms of one variable, and then on the outside we then integrated that with respect to our other variable. This is called an iterated integral, or more commonly we just call it a double integral. Now most of the time when we write it, we're not going to put these brackets on here. Notice how we literally kind of differentiated the fact that we've got brackets on the inside of this integral and then the brackets on the outside. How we would typically write this is we'll just put the two integrals right next to each other. So this would be the double integral of 4xy plus e to the x. Notice our little integration variable terms, we're just going to keep them in order, so whichever one is closest to the function is the one we're doing first, and we'll go with the inside bounds, and then the outside ones will go with the outside bounds. So this would be with respect to y, where that goes from 1 to x, and then dx, where x goes from 0 to 1. So this is how we would more typically write a problem like that. As we're taking a look at a question like this, when we look at other examples, we'll notice that the limits of integration on the inside integral can be those constant functions. So they can be functions of the outside variable of integration. So like these ones can be functions of x, but they can't be functions of y. But then my exterior bounds will be constant bounds in terms of both variables of integration. So typically that means that they're just going to be straight up scalar bounds. In theory, they could be in terms of, if there was like a third variable z here, they could be in terms of a third constant variable with respect to both of them, but most of the time they're scalar bounds. So taking a look at things like that, we can look at, say, for instance, we could have like good examples and bad examples. So a bad example, something that would not be well defined, that wouldn't make sense, is if I did something like the integral from 1 to y of the integral from 3 to x of 4xy plus 1 dy dx. So it might be a little funny to notice at first. So my inside bounds here are fine because we're doing dy, so they're in terms of x. But once I get to the exterior bounds, I no longer want to go back and have it in terms of my other functions. Because at this point, I've already integrated with respect to y. So we've already treated y as a variable. So at this point, we want our bounds to be constant. And we're going to see in a second kind of graphically what this all means, what it's representing in terms of functions on a graph, and we'll kind of get a little bit better picture of why we don't have these function bounds, but we would not do something like this. So something like this is not a good example. A good example is we could keep everything the same, so we could still do 4xy plus 1 dy dx, where we could have y go from 3 to x, and then we could say have the exterior bounds go from something like 4 to 6 would be perfectly fine. So I'm going to switch to another video here in a minute, but what I want to do is focus on this good example and see what it's representing graphically and how it's actually telling us an area problem when we look at the graphs.